Okay, so thanks everyone for being here. I've been already introduced by Odile. I'm Dr. Ilaria Barone. I work at the University of Padua, especially at the Department of Geosciences. And today I'm going to introduce you to the topic of passive seismic methods, and in particular to the ambient seismic noise. So my presentation will be divided into two parts. The first part is more theory, let's say, so I will introduce the methods. And then in the second part, I will just show you a couple of case studies in order to make you understand how we apply these methodologies to the real world. Okay, just a brief introduction to what is ambient seismic noise. Ambient seismic noise includes all the vibrations that are produced by either natural or anthropic sources. Among the natural sources, we do have, of course, earthquakes, but the dominant part of the natural sources are microseisms, and I will introduce this concept in just a slide, okay, in the following slides. Natural sources generally produce very low frequencies, below 1 Hertz. And then we have anthropic sources that are instead all the sources that are human generated. So, of course, we have traffic, so all the cars, all the trains, all industrial operations, and so on. Normally, this type of noise spans over a higher frequency range. So normally we talk about frequency higher than 1 Hertz. So this ambient noise looks rather random, as you may see from these two typical traces. And the idea of passive seismic methods is to try to extract coherent energy from these random signals. So talking about the natural sources, as I said, they are pretty low frequency. There has been these authors, Tanimoto and Anderson, 2023, classified these natural seismic sources into 4 main categories. The first one is the hum. The hum basically includes all the background, the very low frequency background oscillations of the Earth that are mainly excited by the ocean waves. And as you may see, the frequencies are very, very low, spanning from 3 millihertz to 15 millihertz. Then we have the primary and the secondary microseismic ranges. The primary microseismic range includes all the vibrations that are generated from distant ocean waves that are interacting with the seafloor, and the frequencies are between let's say 0.05 Hertz to 0.07 Hertz. Then the secondary microseismic range has been demonstrated to be generated from the wave-wave interactions. It means that when we have different ocean waves traveling in different directions and they cross each other, we generate these secondary microseisms. And the generation is also, it also happens in the nearby oceans, differently from the primary microseisms. This, let's say, type of events span over a wider frequency range, also higher frequency from 0.1 and 0.4 Hertz. And then we have the transient phenomena that include all the transient cyclones, wind-generated ocean waves, tornadoes, and so on, that could generate frequencies that are a little bit higher, even up to 2 Hertz. So we are even over the let's say, normal 1 Hertz limit for the natural sources. What you can see from this plot on the bottom are 3 spectra. So this is a station in the California. This is another station in the East Coast in the United States, and this is a station in Australia. So you can see many curves. These curves correspond to the average noise spectra in the different months of the year. And from this, we can see that we have a very strong seasonal effect. And in particular, in the Northern Hemisphere, we have much higher amplitudes in the months of November, December, January, February. Okay, so this is the winter for the Northern Hemisphere, where we do have many more oceanic storms and so on. While in the Southern Hemisphere, of course, as we expect, we have most of the energy during their winter, which is June, July, August. Another interesting fact of this spectra is that we can clearly recognize the primary microseismic peak and the secondary microseismic peak that in some parts of the year, and especially for this station, is divided into two peaks. Okay, so we could have two different peaks for the secondary microseismic range. So we have seen that we have a strong seasonality, and this seasonality includes the HAM, the primary microseismic, and the secondary microseismic range, not the transient phenomena, which by definition are transient. These seasonal variation will be needed to be taken into account. Talking about the anthropic sources, they are characterized by both a daily and a weekly periodicity, because of course all the human activities are acting during the day and much less during the night, and also more during the weekdays and less during the weekends. Traffic is one of the main sources of anthropic noise, but we could have also, as I said, industrial noise, so industrial machinery, also compressors and pumps act as anthropic sources, and generally these kind of sources cause a monochromatic noise, means focus on single frequencies. A good way to analyze anthropic noise is to compute spectrograms, which are frequency time diagrams, like the one in the bottom. And for example, from this diagram, we can see that during the day, okay, the daily hours, we have much more noise that is focused on, let's say, a range between 8 and 20 hertz, with a peak at 10, 12. We can identify some monochromatic noises that are horizontal lines, like this one at 24 hertz. And we can also identify some vertical lines. Vertical lines means impulsive noise that span over a wide frequency range, but that last a very short time. So these are impulses or very strong but short noises. Here there's another nice example of noise characterization, anthropic noise characterization over a longer period. It's taken from this publication from one of my colleagues. And in particular, these spectrograms refer to the different stations in the Po Plain, spanning from December 19 to April 2020. I think you all remember what happened in that period. We had the pandemic, the COVID-19 pandemic. So related to the pandemic, we had also many restrictions. And so here you can clearly see the weekly periodicity that is normal for anthropic noise, but somehow in this part of the year, we had strange behavior. This weekly periodicity was somehow broken. And if we have a look at the PSD plot, and also to the moving average of this PSD plot, we smooth out the weekly periodicity. So this is the red curve. we can clearly see there has been a drop of the overall energy in January 2020. Then the energy was rising again, and then it was smoothly dropping again. So this period was a period of strong restrictions. So people couldn't move, anthropic activities were somehow reduced. And also in this period, there were restrictions going on. So this plot shows that human activities cause very strong ambient seismic noise, and we can clearly recognize a pattern. Okay, so in this slide, I want to make clear the distinction between an active seismic method and a passive seismic method. In an active seismic method, like also smaller scale acoustic studies, okay, so basically the same thing, just rescaled, we do have a source, we do have a receiver, we generally know the source in terms of shape of the pulse, in terms of location, and in terms of timing. So we record a trace, we see at what time our pulse arrives at the receivers, and so we can have an estimate of the velocity of the medium. Okay, in passive case, we don't have control sources. What we have generally is a pair of receivers or stations, and then we have many sources that are acting everywhere, but we do not know where and when, and also we don't know their signature. So generally, the signature of each of these sources is quite random, like in this case. So the idea of passive methods is actually to analyze the random ambient noise wave field recorded by pairs of stations, and then reconstruct the impulsive response between them. That is also called the Green's function. And so at the end, what we will obtain is a signal like this one, that is the equivalent of the sum of a signal that is recorded in R2 if we have a virtual source in R1, and a signal that is recorded in R1 if we have a virtual source in R2. We will explore a little bit better how we get this kind of signal, of course, but the main concept is this one, retrieving a coherent signal that is similar to an active signal from a random ambient seismic wave field. The technique we use is passive seismic interferometry. But before introducing the technique, I need to introduce the concept of cross-correlation that maybe some of you already know, but since it's the basis of all the interferometric techniques, this needs to be explained and introduced. So cross-correlation is a mathematical operation that combines two signals, and in particular, it is used to measure the similarity between signals. From a mathematical point of view, it can be seen as the integral of the product of two functions, where one function is shifted in time. You can also see this complex conjugation here that you probably can ignore for the moment, because if the signal is real, the complex conjugation doesn't really matter. And generally, we analyze real signals. Okay, so how does that work? Let's suppose we have these two signals, f and g. F is a box function, g is a triangular function. They have some similarities, they're not exactly the same function. When we compute cross-correlation, we take f and we leave it in a fixed position. Then we take g and we start shifting g with respect to f. So we see that we have different combinations, different time lags, okay? And for each of these time lags, what we do, we compute the dot product of the two functions. When we have the maximum of the overlap between the two functions, we have the maximum of the cross correlation. Be careful, because cross correlation is not a commutative operation. So if you compute G, if you correlate G with F or F with G, you don't obtain the same thing. Here we have another example. Again, we have a box function, function X, and we have a Gaussian function Y. The box function has its maximum between 20 and 40 seconds. This Gaussian instead has its maximum between 0 and 20. So in the cross correlation, you will see a maximum at 20, which is the time shift that is needed to have the maximum of the overlap between the two functions. Okay, now I'm going to explain seismic interferometry, and I will follow this Wapner et al. 2010 paper, which is a very nice paper. It's a tutorial of seismic interferometry. So let's suppose we have two stations, one in XA, one in XB, and we have a seismic source that is acting on the left side. This is a plane wave propagating from left to right. And in particular, the seismic source is a Dirac, so it's an impulse. This is the signal that we record at XA, and this is the signal that we record at XB, so the same signal but just delayed. If we cross-correlate this signal with this signal, what we obtain is this signal, which is again a Dirac, but at the time Tb minus Ta. Tb minus Ta is exactly the time that the wave takes to travel from A to B. So this is the equivalent of recording in B something that is produced in XA. Now let's take the case of a plane wave propagating from right to left. Again, this source is a Dirac. This is the signal that is recorded in XA. This is the signal that is recorded in XB. If we cross-correlate this signal with this signal, we obtain this signal, which is a Dirac at a negative time. This negative time is Tb first minus Ta first, which is the time that the wave takes to travel from XB to XA. Again, we have kind of reproduced a virtual source in XB and the signal received in XA. Now, let's combine the two signals. So now let's suppose that we have both a source acting on the left side, propagating towards the right, and a source on the right side, propagating towards the left. So this is the signal that we record in XA, this is the signal that we record in XB, and this is the cross-correlation of the two signals. So now we have the same pulses that we observed before, this peak at Tb minus Ta, and this peak as Tb first minus Ta first. But we also have these two peaks that are cross terms. These cross terms have no physical meaning, and they are there because the source on the left side and the source on the right side have exactly the same shape. They are both Diracs. So when we cross-correlate them, we have something that is non-zero, and that's exactly these cross terms here. Now let's take the case of a noise source. So again, we have a plane wave propagating from left to right, but it's not a Dirac anymore. It's a signal with a certain duration that is kind of random. So this is the signal that we record in XA, and this is the signal recorded in XB, which is basically a delayed version of this signal. If we cross-correlate the signal in XA with the signal in XB, this is what we obtain. So again, we obtain a pulse at a certain time, which is the propagation time from XA to XB. The shape of this pulse is not a Dirac anymore, but it's the result of the autocorrelation of this signal. So it's the correlation of the signal with itself. So that's really interesting because we already got an impulsive response of the system by just cross-correlating signals that are random. Now let's add a source acting from the right side and propagating towards left. And when we cross-correlate the two signals, recording in XA and B, this is what we get. We get a pulse in TA minus TB minus TA and a pulse in TB first minus TA first. We do not have cross terms. And this is because the shape of the pulse produced on the left side and the shape of the pulse produced on the right side is completely different. So the two signals are totally uncorrelated. And that's very good because now from two noise signals, we have obtained the impulsive response of the system. And eventually we could estimate the velocity of propagation of the medium. But we cannot control the origin, the location of the seismic sources. We are not sure that seismic sources are in line with the pair of receivers. They could be everywhere around us, and so they could cover all possible azimuths. So here you have another example with two stations, and then you have all these dots that are noise sources that are evenly distributed in azimuth. First of all, they are distant, okay? Then they are uncorrelated because each noise source has a different shape of the signal, and then they are isotropically distributed in azimuth. If we are in this condition, and if we cross-correlate the signal recorded in XA with the signal recorded in XB for each of these sources, and we plot them as a function of azimuth, this is what we obtain. And if we stack all these traces, so if we sum them, we obtain something like this, which is very similar to what we had before. And this is because all the sources in these regions interact destructively, while the sources in these regions here, you see they are more or less aligned, interact constructively. These regions here are called Fresnel zones and correspond to the sources in these areas. So we have seen that if we have noise sources, even if we don't know them, but if they are all around us with an isotropic illumination and all covering all azimuths, and if they are distant and are correlated, we can retrieve the Green's function, the impulsive response of the system between the two stations. And something important is that we need this isotropic illumination covering all azimuth to have this Green's function symmetric. So what happens when we don't have this isotropic illumination, but we have sources that are mainly on one side of the receiver array, of the receiver pair? I've done some simulations, and okay, here you have many receivers, the ones in blue, that cover a rectangular area. And then we have all these noise sources that are evenly distributed in azimuth at a distance of 100 meters. What is shown on the right side is are all the cross-correlation functions that correspond to the receiver pairs that have in common this virtual source. So we have basically selected all the receivers on the diagonal of this rectangle and computed the cross correlation with this source and all these receivers, okay? And then we have ordered the cross correlations as a function of distance from the virtual source. And in this situation, everything is really nice because we can see these peaks, all the cross correlations are symmetric. And since we have distance and time, we can easily get the velocity of propagation of the medium. Now, first of all, I also want to show you what happens if we compute the cross correlation for all receiver pairs, taking this as virtual source, but now we take all the receiver pairs for all the receivers in these rectangular areas. And here I'm going to show you an animation that takes all the horizontal slices, so time slices, and that will show you the propagation of the wave from the virtual source. And this is more or less as we expect it to be. So we have propagation acting from this virtual source, and it's exactly as if we had a real source in this location. Then this is the case where we have an unfortunate case where we have sources only on one side of the array. And these are the cross correlations that we obtain. Of course, if we have something like this, it is really difficult to say which is the velocity of propagation of the medium. And if we have a look at the propagation from the virtual source, instead of having a clear propagation from this point, we kind of see propagation from left to right, which is, of course, the result of having sources that are only on one side of the array. So this is a demonstration that we really need to have sources everywhere, covering all possible azimuths. But in nature, this kind of distribution is not happening, or its condition is hardly met. Especially, we cannot control it. But what we can do is to check which is the actual noise source distribution. And we have different possibilities to do that. Either we somehow measure the symmetry of the cross correlation function, or as in this case here, we compute what is called a beam spectrum. This is the beam forming technique. This is a rather old technique and gives you this kind of spectra. This is the wave number in direction X. This is the wave number in direction Y. And this is a spectrum that is valid for one single frequency. And from this spectrum, you can see that we have a preferential orientation of the noise. So the noise is coming in this specific case from northeast. Although there is still some noise also in the other direction, just less powerful. The fact that we have kind of a circle is because the radius of the circle gives us an indication of the velocity of propagation of the medium. So with beams forming, this is a very powerful technique because we have both the directionality of the noise sources, but also an indication of the velocity of propagation of the medium. The problem is that we need to have many stations to be able to compute a clean spectrum like this one. In the case we have directional sources, we could still use passive seismic interferometry. Some authors like Delaney et al. 2006 17 have attempted to quantify and correct for the travel time biases caused by this uneven source distribution. So it is possible, but it's not straightforward. What are the countermeasures? First of all, nature is somehow mitigating this uneven source distribution by causing scattering. So scattering is generated whenever we have heterogeneities in the medium that at our scale are maybe faults or some other kind of heterogeneities in the subsurface. And so when we have heterogeneities, we have scattering that redirects the seismic energy in different directions and somehow mitigates the problem. But we can also do something at the processing stage. So if you have a look at this workflow, this is the workflow to obtain, the first part of the workflow to obtain cross-correlation functions from ambient noise. What we generally do, we divide our total ambient noise record that could be quite long in small windows, generally overlapping windows. And for each window, we apply a pre-processing that includes the removal of the instrument response, the demean, the despiking, and so on. And then we apply a normalization that could be done either in time domain, such as the 1-bit normalization, or in the spectral domain, such as spectral whitening. Spectral whitening is basically a flattening of the spectrum of the noise, such as in this case. Here we have the original spectrum, and this is the spectrum after spectral whitening. You see there's a common level here, although it's not very smooth, okay? And then there's a ramp down. Why is this good is, let's say, why is this compensating for the problem of not having a homogeneous distribution of the noise sources? Because we could have strong transient signals that come from one preferential direction, and these strong transient signals could be short in time, so they could affect only a few windows, and by doing that, we somehow bring the energy of that specific window to a common level. And then finally, what we can do is to average the positive lag cross-correlation with the time-flipped negative lag cross-correlation. This is also something that is normally done, and that somehow compensates for this asymmetry of the cross-correlation function. After applying pre-processing and normalization to each single window, we compute cross-correlation for pairs of stations. And then what we do at the end, we stack all the cross-correlations to get one single cross-correlation for the whole recording period. That could be several hours, several weeks, several months, or even years. Okay, so it depends, of course, on the frequency range that we analyze and on the scale of application. Very importantly is that if you know that you are analyzing a frequency range where you have seasonalities, you should try to use an ambient noise record that is at least as long as the period of the seasonality. So in the case of the microseismic primary or secondary microseismic range, we should try to use at least 1 year of data to get rid of the seasonality. And then estimate the velocities of propagation. So in principle, when we apply seismic interferometry, what we reconstruct is mainly the surface wave field, because the surface wave field is dominant in the ambient noise. I don't know how familiar you are with surface waves, but they are waves that travel at the boundary, let's say at the Earth's surface, okay, the surface of the medium. And their main characteristic is dispersion. Dispersion means that each single frequency travels with a different velocity because they penetrate, low frequency penetrate deeper than high frequencies. Since we generally have a higher velocity at greater depths, then it means that the low frequency will travel faster than the high frequencies. And so instead of getting just one value for the velocity of the medium, what we get is a dispersion curve, which is actually the relation between velocity and frequency. From this plot, it is very clear this characteristic of dispersion of surface waves, because this is the same cross-correlation function that has been bandpassed in different frequency bands. And so you see that the low frequency travels much faster than the high frequencies. And then which velocity do we measure? Here it's written measure group and or phase velocity. What are group and phase velocities? Here I have put an animation where I hope you can understand the difference between phase and group velocities. Phase velocity is the velocity of propagation of each single phase. So a phase is basically one single peak in this animation, while the group velocity is the velocity of propagation of the envelope of the wave. So if we look at this plot, at this animation here, we see that each individual peak has a certain propagation velocity, the one in red, and then the blue point is indicating the center of the envelope of this wave, and this is the group velocity. We can have many combinations of phase velocity being higher than group velocity, lower than group velocity, equal to group velocity, but in general, when talking about surface waves, this is the common situation where the phase velocity is higher than the group velocity. It is not that important which velocity we measure, because both phase and group velocity are strongly dependent on the shear wave velocity of the medium, in particular on the depth distribution of the shear wave velocity, which is our last objective. This is what we want to get at the end. We have several methodologies to measure either group velocities or phase velocities from cross-correlation functions. For example, here I name just a couple of methods. The cross-spectral analysis is analyzing the real part of the cross-spectrum, which is the spectrum of the cross-correlation, and derives phase velocities by analyzing all the zero crossings of this function. So every time this function crosses the zero, we have a frequency value and a number of associated possible velocities for the medium. And what we need to do in this method is to try to pick the most plausible ones. And then we have the frequency time analysis, or STAN, which is also a rather old method, very used. In this case, what we get is a spectrum like this one. On one axis, we have the group velocity. On the other axis, we have the frequency. And by picking the maxima in this spectrum, we get the group velocity dispersion curve. Of course, this kind of analysis are done for each pair of receivers. And if we have a network, that's generally the case in seismology, we have a certain number of stations deployed in a certain area. What we can do is to measure the phase and or the group velocity for each receiver pair. So we have a lot of information that we need to recombine somehow. And the way we recombine it, spatially, is the application of surface wave tomography. And what you get at the end is a phase velocity or a group velocity map, like this one, for each single frequency of analysis. And then, since you have several maps or several frequencies, what you can do is to, for each single location in the map, you can extract the phase or group velocity values and reconstruct a dispersion curve, a local dispersion curve. And then through a process that is called depth inversion, you get the shear wave velocity profile as a function of depth. We repeat the operation for all the points in this map. And at the end, what we get is a 3D shear wave velocity model, like the one displayed here. These are just vertical sections of this 3D model in order to show the different structures in the subsurface. What do we do with this 3D shear wave velocity model? It depends on the application. For example, in this case, the authors have done some structural interpretation. So they have identified the position of basins and structures, geological structures, and so on. In other applications, we could use these models to locate earthquakes, because of course, to locate an earthquake, we need a velocity model. And then we could also, at much smaller scales, we could identify buried manufactures such as archaeological structures, and we'll see a case study in the second part of this presentation. I've talked about surface wave interferometry, passive seismic interferometry to reconstruct surface waves, because the surface waves are dominating the ambient noise field, but we could also use interferometry to reconstruct reflections, so body wave reflections. And in this case, what we need to have is not plane waves propagating from different azimuths, but sources that are deep down, so sources that are in the deep layers in the subsurface that are acting, propagating from upwards, let's say, okay, from down to the surface. So let's take this example. We have two stations, A and B. We have a source in the subsurface, and the signal that we record in A is this one. Then we also have a scatterer, which is this point here, that can reflect back the energy to the surface. So in B, what we register is the effect of the wave propagating from the source to A, down to the reflector, to the scatterer, and back to the surface. So we have a delayed version of the wave recorded in A. And if we cross-correlate these two signals, what we get at the end is the signal that is basically the same as having a virtual source in A that propagates down and is reflected back in B. So again, with cross-correlation, we could remove the paths from the source to the first receiver. So at the end, what we get is the reflection from A to B. And again, we cannot control the location of the sources. in the subsurface, so the sources could be everywhere along this line. And if we make the same exercise we did before for the horizontally propagating waves, if we plot all the cross correlations for all the possible sources along this line, this is what we get. And if we stack all these traces, we finally have these traces, because we had constructive interference in this area, which is the Fresnel zone again. The Fresnel zone in this case is, includes all the sources in this area. And this is a very convenient method when we have single stations. So let's suppose we have just one station here, and we have all these noise sources in the subsurface. The energy is going up and then is reflected down and then back to the surface, because here we have a reflector. If we apply autocorrelation, so if we correlate the signal, the noise signal that we record in R with itself, what we get is something like this. So we always have a maximum at 0 by definition of the autocorrelation, but we also have, in this case, a minimum at a certain time that corresponds to the time that the wave takes to go from the source, actually the receiver, okay, to the reflector and back to the receiver. So it's like recording signal in R that has been generated by virtual source in the same location. And I said it's very convenient because in some cases we can only have one station, for example, on Mars. And this is one of the methods that have been used on the seismic data recorded by the seismic sensors that have been installed in Mars to get the structure, the interior structure of Mars. And finally, and then we have a break, Coda wave interferometry. I'm not going to explain it again because I think you had many lectures on this topic, but I just want to mention that we can also do dynamic analysis with the ambient seismic noise. And in particular, we could compute the cross correlation for different time intervals. For example, we could compute the noise cross correlations on a daily basis and retrieve many cross correlation functions for many days, and then apply Coda wave interferometry to get possible velocity variations or structural variations in the medium. The choice of analyzing the signal in the Coda is to get rid of possible effects due to the noise source directionality. And this is because the Coda, by definition, is the effect of multiple scattering in the medium. The scattering should redirect the ambient noise into different directions, and so we should not have too many problems related to seasonality of the noise source and so on. That's it for first part of this presentation. And if you have any questions, of course, I'm very happy to take them.
Thank you very much, Ilaria. It was very clear, very nice. So we have room for discussion.
I have a question.
Yes, maybe I will take the question of Jasmine later, okay? So I just want to show you a couple of case studies that are quite different in terms of scale of application and also motivation for the study. The first one refers to a microseismic monitoring network. If you're not familiar with the concept of microseismic monitoring, it's basically something needed when we have operations, when we inject or produce fluids in the subsurface, such as for gas storage or geothermal activities and so on. Okay, so every time we inject some fluid or produce some fluid in subsurface, we could eventually generate earthquakes, and this is really what we do not want to have. And so we need to have always a microseismic monitoring network that is composed of several stations that can be at the surface, can be also in wells. And this set of stations is needed to detect possible, even small earthquakes in the vicinity of the reservoir that are not detected by the national networks, which are rather sparse, and eventually stop the operations if we see that something is going on. Of course, we don't want just to detect the earthquakes, but we also want to locate them correctly to see if they come from the reservoir or if they come from somewhere else. And to correctly locate a seismic earthquake, we need to have a good signal-to-noise ratio to pick the P and S phases. We need a good location algorithm, but of course, we need a good velocity model. Okay, both P wave velocity and S wave velocity models. Talking about the P wave velocities, we generally can retrieve a P wave velocity model quite easily using reflection seismic. But for the S waves, it's a little bit more tricky. And so generally what is done is to take regional models from the literature that are good at, let's say, a regional scale, but are not very representative of a specific site, of the local condition of a site. Or we use well-log data that instead is very precise, but it refers to single locations, so it may be not representative of the average conditions around the reservoir. And in the worst case, but this is actually done very often, what we do, we just apply an empirical VP-VS relations, and so we get VS from VP empirically. Of course, we want to do something better than this, and so our group tried to reconstruct an S wave velocity model for relocation of small earthquakes, starting from passive noise. The site is located in the Po plain, so we don't have any topographic problem. All the stations are at the same elevation. The site was a gas storage site. We have 8 seismic stations. Some of them are located at the surface, the one in red, and some of them are located in, in shallow boreholes at about 150 meters depth. The seismometers are 3-component short period seismometers. And just to give you an idea about the size of the network, the interstation distances span between 2.2 and 13.5 kilometers. We have analyzed in this case 2 years of continuous data, only the vertical component of motion. First of all, we did some say preliminary analysis of the ambient seismic wave field. And in particular, we have computed spectrograms for the 2 years for the different stations. And here you have a station that is placed on the surface and one in the borehole, in the shallow borehole. And you see that they present more or less, they show more or less the same behavior. In particular, we can distinguish the noise in 3 frequency ranges. The first one is between 0.1 and 0.25 Hertz. That is related, if you remember, to the secondary microseismic range. So it is affected by definition by a strong seasonality, and that's what we see. because during the winter we have a lot of noise, and during the summer we have much less noise. Then we have an intermediate range between 0.25 and 0.5 that is characterized mainly by sparse amplitude peaks that have a duration of typically 2 to 3 days. These peaks are from the literature related to local wind-generated sea waves in close by seas and oceans. And we will see in the following slides that it's exactly like this, so we verified this. And then finally, the range above 0.5 Hertz. As you may see, there is a pattern that is a weekly pattern. This weekly pattern we have seen is typical of the anthropic noise. So it means that above 0.5 Hertz, we already see some anthropic noise that generally is characterized by frequencies higher than 1 Hertz. Okay, so this is the demonstration that the peaks that we see in the intermediate range are related to wind-generated sea waves. So we have taken a horizontal section of the spectrogram at 0.3 Hertz, that is this one. And then we have downloaded the sea wave, the sea wave 8 at two stations, one in Ancona in the Adriatic Sea, and one in La Spezia in the Tyrrhenian Sea. The network is around here. We cannot disclose the exact location. And so you can see that, especially with the wave height of registered in Ancona in the Adriatic Sea, we have a very strong correlation between the noise recorded in the spectrogram and the wave height. So probably most of this noise, most of these events that you see are just, let's say, sea storms happening mostly in the Adriatic Sea. We also have some correlation with the storms in the Tyrrhenian Sea. Then the directionality, we have investigated if we had a strong directionalities by analyzing the symmetry of the cross correlations for the different station pairs, and these diagrams show exactly this for different frequency ranges. And we have done this exercise for the month of January and the month of July. And as you may see, let's say for all frequency values, we have energy mostly from everywhere, from all azimuths, but we have some stronger directionality in January. So we see that most of the energy is coming from the northwest. That means probably from the Atlantic Ocean, where in winter we have strong storms. This is a typical pattern at this frequency range. And we see much less directionality in summer for the same frequency. Despite that, I think we have kind of a good distribution of the noise sources. And this is the processing flow that we have applied to get the cross-correlation functions. We have analyzed windows of 30 minutes and with an overlap of 15 minutes. For each window, we have applied a pre-processing that includes the spiking at the mean, the removal of the response of the sensor. Then we have applied spectral whitening, so a normalization in the frequency domain, cross-correlation for each pair of stations, and then stack of the different windows for the whole 2 years of data. And finally, we have averaged the positive lags with the negative lags, and that's what we got. You can also see from here that there's no energy below this line, and above this line and below this line, because we also applied, and I didn't mention in this flow, a velocity filter. It means that we have applied a mute in time domain for all the velocities that are non-realistic, okay, too high and too low. Okay, so starting from those cross correlations, we have extracted, in this case, both group velocities and phase velocities. For the group velocities, we've used the TAM method, frequency time analysis, and here you have two velocity frequency spectra for two example pairs. And then we have also extracted the phase velocity dispersion curves for the same pairs. Here you have the graphs. So these are the cross spectra, and these are the corresponding peaked velocities, the red dots. Then we have recombined all the velocity information for different pairs, especially using surface wave tomography, both for group velocities. So these are all the group velocity maps for the different frequencies, and the phase velocity maps. So from these, you can clearly see the dispersion, because low frequencies are characterized by much higher velocities than higher frequencies, both for group and phase velocities, but we cannot really appreciate strong velocity variations. And so for this reason, we decided to invert all the dispersion curves and then apply an average to get a 1D model. And that's what we got. So in gray, these are all the inverted shear wave velocity profiles for the different locations in the network, and this is the average curve. So this average model is exactly what we needed to locate local seismic earthquakes. And on the right side, we also computed the standard deviations, and then from that, the percentage lateral variability of velocities. This is just a measure of how much the velocities vary laterally in the network at the different depths. Okay, this is the first case study. Now, I'm going to show you probably more interesting case study that is at a very small scale, at an engineering scale, and it refers to the Scrovegni Chapel. The Scrovegni Chapel is located in Padua, and it's a very famous monument recently included in the UNESCO World Heritage List. And maybe from outside, you cannot really understand the importance of the chapel, but if you go inside, you see this fantastic Giotto's fresco cycle, and you understand why it's in the UNESCO World Heritage List. Talking about the area where the chapel is located, it's a very complex area from an archaeological point of view, because it hosts remains of different historical buildings of different times, including a Roman amphitheater. We started to do this acquisition, this study in general, because we wanted to answer to some open questions, including the role of the crypt of the chapel, the actual position of the radial walls of the amphitheater, the possible presence of a gallery along the major axis of the amphitheater, and we will see that in detail later on. And for this purpose, we have designed an acquisition that is a very, very dense seismic acquisition for this scale, because we have used almost 1,500 seismic nodes on two rectangular areas, one inside the amphitheater and one outside. And we have performed both active analysis and passive analysis. This is just a satellite image to show you the location of the chapel with respect to the Roman amphitheater. So this is the elliptical middle wall of the amphitheater. You can see that the facade of the chapel stands on this wall. So there is a strong interaction between the two monuments. And then this picture is also to show you where the chapel is located with respect to the city. This is the city center of Padua. On the north side, we have the train station. Especially what's very important is this road here, which is the main road where there are a lot of trams and buses running during the day. On the other hand, on this side, this is a quiet area because there's a park, there's a river, and so on. So these are maps that show you all the excavation phase, archaeological excavation phases. This is the chapel. This is again the Roman amphitheater. So in gray and in black, you see all the remains that have been brought to light in the different excavation phases. And here, this is the palace. A palace that was actually originally adjacent to the chapel. And okay, something interesting to point out is that these are the radial walls. Okay, the radial walls were found only partially on this side. No radial walls were ever found on this side. And from this small amount of remains, people have tried to reconstruct the scheme of the original amphitheater. And the direction of these radial walls is somehow not corresponding to the direction of the chapel, of the walls of the chapel. And this is something that the archaeologists were trying to investigate. And then, as I said before, archaeologists also wanted to see if there was a gallery along this major axis. Okay, so this is the acquisition scheme. The two rectangular areas, the one inside the amphitheater was characterized by a receiver spacing of 1.5 meters, and the one outside a spacing of 1 meter, so even denser. These red stars are all the active shot locations. So we have in total 38 shot locations where the source is a weight drop. So it's just 70 kilos released from an height of 1.5 meters. And as for the passive acquisitions, we recorded about 22 hours of data. So it's completely different from the other case study where we were recording for 2 years. And we decided to cross-correlate all the noise recorded in all the receivers with the sources that are on the edges of these rectangular areas. So these are all the sources that will become virtual sources. There are 94 for the internal rectangle and 128 for the external. This is a picture that shows you the seismic nodes that are very small, and they were buried in the earth like in this way. And this is instead the weight drop, so the active source. Okay, now I'm going to show two animations to give a feeling of the difference between the active wave field and the passive wave field. So, sorry. On the left side, this cross gives you the location of an active shot. Then we have a rectangle of receiver here and another rectangle here. So here I'm going to show you the propagation from this active shot location. So this is possible since we have a lot of receivers. So we have a dense cover of receivers everywhere. And on this side, I'm going to show you instead a passive seismic recording. So before cross-correlation, the raw passive data. Okay, so what can we see here? First of all, if you look at this wavefront, this is not circular, there is a distortion, and this is probably caused by some velocity anomaly in this area. Then we can also see that the amplitudes in this rectangle are much higher than the amplitudes here, and this is because this is the wall of the amphitheater. There's this amphitheater that is acting as a screen, so it's preventing most of the energy from propagating from one side to the other side. Please notice also the scale that is different because, of course, ambient noise, although it's quite strong in that area, is not as strong as the active wave field. And also, I think you may have noticed that there is a preferential direction of propagation of the ambient noise from this side. And remember, on this side, we had the main road. Finally, what I want you to see is that in terms of frequency content, the active data is characterized by a central frequency of about 30 Hertz, while the passive data is characterized by a central frequency of about 10 Hertz. So we have somehow a complementary frequency content. These are two spectrograms, one for a receiver inside the amphitheater and one outside. And you can see that we have most of the noise happening during the day. You can recognize some monochromatic noise that is present both inside and outside. And these vertical lines are corresponding to the time where we did the active acquisition. So basically, these vertical lines are the active shots. In order to characterize the noise wave field in terms of directionality, we have applied beamforming. So you can see, okay, I have applied beamforming on local coordinates, and so then I had to rotate this map, but you can clearly see that if we apply beamforming for daytime hours, we have a preferential direction of the noise from northwest. Although if we do the same exercise during the night, we have a preferential direction from southeast. So from northwest, we know there's the street. From southeast, we don't really know what's happening. But that was not a bad thing, because somehow it's compensating, let's say it's complementing the direction of origin of this noise. And if we apply beamforming for the whole 22 hours, we have a very similar picture of the daytime beam spectrum, because the daytime noise is dominant. But when we apply spectral normalization, so the spectral whitening, we retrieve a quasi-isotropic wave field, because somehow we balance the night noise that is of low energy with the daytime noise that is of higher energy. And so finally we retrieve noise from everywhere with almost the same intensity. This is a comparison. This is the processing workflow that we have applied, very similar to the previous one, but now the windows are of length 5 seconds. We apply the bandpass, spectral widening, cross correlation, stacking, and the average of positive and negative lags. And this is a comparison of an active shot gather with a passive shot gather, more or less in the same location. And this is the 2D FFT of those gathers, so the frequency wave number spectra. And here you can clearly see that, again, the passive noise is complementary to the active signal, because it is characterized by lower frequencies. There is a range from, let's say, 10 to 20 Hertz, where we have some overlap of energy. And that's where we focused on the comparison between the two. Again, animations, let's say the wave propagation from this virtual source for the rectangle inside the amphitheater. And things work pretty well. And the same exercise for the rectangle outside the amphitheater. In this case, let's say it works well, but not as well as before. And we will see that in a while. Okay, these are some results. So I'm not going to detail the processing to get the phase velocity maps, but I just give you directly the results. So this is a phase velocity map for the rectangle inside the amphitheater for the passive data analysis. And this is the same map that we obtain using only the active data. Okay, so we see that there are some common patterns, especially we see a low velocity anomaly in the middle for both maps, but for the active case, the resolution is quite poor. If we look at the standard deviations, so the errors associated to this analysis, the standard deviations for the passive data are lower than the active data. And this is probably due to the fact that we used many more virtual sources than active sources. So this is a map that shows the number of measures used for the analysis and look at the different scale. This is a plot that gives you the standard deviations, the average standard deviations for the different frequencies of analysis for the passive data analysis and the active data analysis. So in this range where we did both analysis, active and passive, we can clearly see that the passive analysis show lower standard deviations. So let's say they give a more accurate representation of the subsoil structures. We repeated the same analysis for the rectangle outside the amphitheater, and in this case, something is not working. From the active analysis, although again the resolution is quite poor, we could see some structures, linear structures here, that have been interpreted as real structures, foundations of all the old structures actually. And in the passive map, this is not very clear. Instead, what we see is some kind of high velocity and low velocity anomaly on this side. And if we look at the standard deviations, in this case, we have a reverse situation because the standard deviations associated to the passive analysis are much higher than the active ones, even though we have used many more virtual sources than active sources. And this problem is quite clear also if we look at the average standard deviations for the passive and the active analysis. So in the common frequency range, we have the standard deviations of the passive analysis that start increasing exponentially. So something is going is wrong with the passive analysis as long as we increase the frequency. And our suspect is that the wall of the amphitheater somehow is too close to the receiver array and is somehow acting as a secondary set of seismic sources. Means that the noise is coming and then it is redirected from the wall. So it's like having a set of linear sources very close to the receiver array. And this is one of the assumptions. So this breaks one of the assumptions of seismic interferometry. Remember, we needed to have distant, uncorrelated noise sources And of course, this is not distant. So finally, what we did, we only took the result of the passive analysis for the rectangle inside the amphitheater. And this is the final 3D model, shear wave velocity model that we obtained on the left side with only active data, and on the right side by including the passive data. So let's say integrating active and passive data. And you may see that on the shallow part, we get very similar results, but in the deep part, the model has completely changed. And this is because the passive data is characterized by low frequencies, and low frequencies are sensitive to deeper layers. And so we are somehow constraining much better the subsoil information at depth. Okay, so this is the end of my talk. To conclude, we have seen that passive seismic methods are either a cheap alternative to active methods or a very good complement to active methods. The main application of passive seismic methods is to reconstruct surface wave signal, and from that to get information on shear wave velocity distribution in the Earth that later can be used either to identify structures or to relocate earthquakes. We have seen that it's also possible to reconstruct reflections and to perform dynamic analysis, such as with the Coda wave interferometry. Remember the prerequisites of the application of the method, which are to have distant uncorrelated sources with an isotropic distribution in azimuth. Talking about the processing, what we should always do is to perform a preliminary noise characterization through spectrograms with beamforming to see the distribution of the noise, both in time and in space. And then apply normalizations, either a time domain normalization or a frequency domain normalization. And finally, stacking the data over a sufficiently long period. And so I just conclude my talk by saying that what we need to do with passive methods is just to listen to the Earth, and that's it. So thanks a lot. I'm very happy to take all your questions.
Thank you very much, Ilaria. It was very interesting. And the images you got from